Hi class, welcome to exercise 7K, direct and inverse proportions and other rates of change. And I should also mention that this is exercise 7L in the old book. So in this lesson, your examples and pre-learning will be example 25, finding and using direct variation rule. And your pre-learning for this example will be question 1A and 2 in the new book, and question 3 in the old book. And then we'll do example 26, finding and using an inverse proportion rate. And your pre-learning for this example will be question 1B and question 3 in the new book, and question 4 in the old book. And then finally, we'll do example 27, matching descriptions to distance time graphs. And your pre-learning for this example will be question 4 in the new book or question 5 in the old book. So some of this lesson is going to seem a little bit simple at different stages, but you really need to focus on grasping the concepts, because the second half of this lesson is extremely important and key concept for your VCE methods. Alright, we'll see you in the introduction. So the first part of this lesson is all about defining the relationships between variables. And the first one is where we have one variable that's equal to a constant times another variable. In this case, we'll say y equals k times x. And if I just paste in these axes, then if this is x and this is y, then this is always going to be a straight line, and y is going to be equal to k when x is 1. And it really doesn't matter what k is, it's just going to change the angle of that slope. So we just say that y is proportional to x. And that weird looking symbol there, that just means proportional. So the term for this is directly proportional relationship. And this is a straight line through the origin, which is essentially the same graph for any k. And as I said before, the only difference would be the amount of angle. And another reason why we'd say that it's directly proportional is that the difference between the y values is directly related to the difference between the x values. Okay, and the other relationship we're going to look at today is the type of graph where two variables times each other equal a constant. So in this case, I'm going to use x and y again. So we'd say that y times x is equal to k. And it doesn't take a genius to realize that if I readjusted that, that means that y is equal to k divided by x. All I've done there is divide both sides by x. So we would say that y, in this case, is proportional to 1 on x. And if I paste in the axes again, and I'll call this one x and this one y, and with this set up in the axes, it's definitely y is proportional to 1 on x. But I could have easily called the bottom axis y and the top one x, and we could say that x is proportional to 1 on y. Okay, and that's just because, if I do a little side note here, if we look at the initial equation up the top there, if I divided both sides by y, we'd say that x is equal to k divided by y. So it's sort of the same thing, right? So we've just done hyperbolas, so you'll know that the graph will look a little bit like this. And because we're multiplying it by k, where x is 1, y will be k, but also where x is k, y will be 1. So for this relationship, we would say that x and y are inversely proportional. And that's because y is proportional to the multiplicative inverse of x and vice versa. And as I said, this will give us a hyperbola with some scaling. And for any point on this curve, the product of the variables is a constant. The next part of this lesson is all about gradient or rate of change. And this is the concept I was talking about at the start of the lesson that is key to VCE. So let's start with what we do know, and that is a gradient in relationship to a linear graph. So if we had a line y equals mx, and we fixed 2 points on it, and between those 2 points we considered the change in y and the change in x. And the gradient was m, which was the change in y divided by the change in x. So that was for a straight line, but what about some weird curvy graph like this one? Well, we could find the gradients at any point we wanted. We can see that there isn't a constant rate of change here. It's all over the place. So we would need to find the gradient at any particular point. So for example, you could see that we have a steep negative gradient here, and a flat one here, and a flat one here. And there really is only one point that goes exactly through the graph at the same direction at that point. These are called tangents, and next year you're going to learn all about these tangents. So I also want you to recall from linear graphs that if our line was pointing up, we called that a positive gradient because it was becoming more. And then if it was pointing down, we called it a negative gradient because it was becoming less. And then if it was flat, we would say it had a zero gradient because it's not changing. And today's lesson, we're going to talk about the size of gradients. And it's important that you realize that it's not related to whether or not the gradient is positive or negative. In other words, this steep positive gradient is bigger than this flattish positive gradient. And at the same time, the gradient of this steeper negative slope is bigger than the gradient of this shallow slope. And that's because these steeper ones on the left here are changing a lot, and these shallow ones on the right here are just changing a little bit. Now, gradient can also tell us about accelerating, because in today's lesson, we're going to look at these time versus distance graphs. And so the change in distance over time is the speed I'm going at, right? So if we could graph my distance from home with a graph like this, then the gradient at these 3 points would look a bit like this, right? You can see each one is sitting right on the line. So that would mean that my gradient is changing like this. With the first gradient being here, then you can see the next one has a slope like this. And finally, the last one there has a slope more like this. So not only is my position changing in time, the amount of change is changing in time. And so we'd say that the size of gradient is increasing, which means my speed is changing, which is why we say accelerating. Similarly, if we were to speak about decelerating, then we'll find that the size of gradient will be decreasing. So let's draw a little graph of me traveling away from home to represent that. So at this point here, the gradient would look like this. And at this point, we'd have this gradient. And at the top point here, we'd have something like this. So you can see that they're straight lines, right? That sort of represent that point. So our gradient is changing like this, where it starts off steeper and slowly gets shallower. So of course, when we're talking about traveling between 2 points, the rate of change is my speed, right? And my speed is getting less as time increases. When we work on these time distance graphs, we've got 3 key bits of information that we'd like you to focus on. So firstly, is it overall positive or negative distance? So when we look at the graph from start to finish, does the distance increase? Because if it does, we'd say that it's a positive gradient, or we're moving in a positive direction. And if the distance is decreasing, we'd say it's negative direction. Then we're going to focus on whether or not our change in position is slow or rapid. So if the graph is steep, there's a big change in distance per time unit, which means that the speed is fast. If the graph is not steep, then the speed is slow. And then finally, are we accelerating or decelerating? And obviously, if my speed is increasing, we're accelerating, and if it's decreasing, we're decelerating. So this might not feel like a lot of information right now, but all possible situations will be covered in the example I do later. And with that, that's the end of the introduction. So if you want to warm up before we get into our other examples, pause your video now and do the building understanding questions if you have the new book, which translates to questions 1 and 2 if you have the old book. And then we'll see you in that next section. When we have 2 variables, x and y, and y is equal to k times x, we describe that as y is proportional to x. So this will just be a linear graph that goes through the origin, and it doesn't matter if k is different, it'll always be the same family of graphs. And the key reason for describing this as directly proportional is if I was to quickly graph y equals kx, and then if we were to pick out 2 points a and b for x values, And if we look at the relationship between the 2 points on the graph for these x values, the change in x can be described by this distance here, and the change in x will be b minus a. And then if we were to look at the change in y, then it's that blue distance there. And the y value in the first point on the left here would be k times a, and the y value in the second point would be k times b. So in this situation, the change in y would be k times b minus k times a. And if I factor out the k, that's equal to k times b minus a. And so the change in y is just a multiple of the change in x. So therefore the change in y is directly proportional to the change in x. So we can use these facts and some simple algebra to find k given matching values of the two variables. Or if we're given k and the value of one of the variables, what is the matching value of the other variable? Alright, let's get onto that in example 25, where we have a variable m that is directly proportional to h. And m is equal to 90 when h is equal to 20. So in part A, we're going to determine the relationship between m and h. So firstly, we know that m is directly proportional to h because we're told that in the question. So that means that we know that m is equal to some k times h. And because we know that m is equal to 90 when h is 20, that means we've got 90 equals k times 20. And that's just subbing in this values were given in the question. So if I divide both sides by 20, 90 on 20 equals k. And so they've both got a common factor of 10. So it's going to look a lot nicer if I put the k on the left. So we've got k equals 9 on 2. And because we now know what k is, we can define the relationship between m and h as m is equal to 9 on 2 times h. So we've now got the value of k, and part B wants us to find out what's the value of m when h is 16. So because m is equal to 9 on 2 times h, and we want to know what m is when h is 16. So the 2 will cancel with the 16 to make 8. So that means that m has to equal 9 times 8, which is 72. Therefore, when h is 16, m is 72. Cool. Alright, let's go to part C, where we're going to find h when m equals 10. So of course it doesn't matter which way we're going here. We've found an m value with a h value. This time we're finding a h value with an m value. So just start off with the equation of m equals 9 on 2h. Then we'll sub in our 10 for m. Then if we divide both sides by 9 on 2, that's the same as multiplying it by 2 on 9. So we've got 20 on 9 equals h. And we can't really simplify that anymore, can we? Other than maybe make a mixed number. So the value of h when m equals 10 is 20 on 9. Alright, we should make a note here that when y is proportional to x, that means that y is equal to k on x, right? And it doesn't take much algebra to realize that that means that x is equal to 1 on k times y. So because 1 on k is just a number, then x is also directly proportional to y as well. And so if y is directly proportional to x, then x is also directly proportional to y. Alright, now it's your turn, so pause that video, do questions 1a and 2 if you have the new book, and questions 3 if you have the old book. Alright, don't forget 1b is for the next section, so just do 1a if you have the new book. Alright, we'll see you in that section when you're done. When y is equal to k on x, then we say that y is proportional to 1 on x. This will create a hyperbola that is scaled by k, and just like the direct variation rules, k can be different, but we're going to end up with the same family of graphs. So let me demonstrate the key point to this by drawing the graph y equals k on x. If I was to create 2 points using x values a and b, and the change in x would be this distance here, right? Or in other words, the change in x will be b minus a. And for these 2 points, the change in y will be this distance here. So using the formula y equals k on x, the change in y will be k on b minus k on a. And to make both of these fractions have the same denominator, I'd have to multiply k on b by A in the top and the bottom, and K on A by B in the top and the bottom, and we'd end up with Ka minus Kb on Ba. And the A and the B are both multiplied by K and both divided by AB, so I could rewrite that factoring out the K on AB. And if you have a look at the change in X again, we have got some factor times the inverse of that statement, or the negative version. So that's why we will say the change in Y is inversely proportional to the change in X, i.e. we've got a B minus A versus an A minus B. And in this section, we're going to find a K when we're given matching values of two variables. And also, if we're given a K and the value of one of the variables, we'll find the matching value of the other variable. Alright, let's get on to that with the example 26, where X and Y are inversely proportional and Y is equal to 6 when X is equal to 10. Okay, so part A, we've got to find the constant K and write out the rule. And what they mean by that is because Y is inversely proportional to X, then Y has to equal K on X. So that means that 6 has to equal K on 10, just by subbing in the values Y equals 6 and X equals 10. So multiplying both sides by 10 means that K equals 60. So therefore our rule is Y equals 60 on X, or you could even write it as X times Y equals 60. Alright, let's move on to part B, where we're going to find Y when X is equal to 15. And of course we're using the same rule, right? So Y is equal to K on X, which means Y is equal to 60 on X. And that means that Y is equal to 60 on 15 when we sub in X equals 15. And my hand seems to say 16 when I mean 60. Alright, so 60 divided by 15 is just 4. So therefore when X is 15, Y has to equal 4. Okay, it's nice and easy. Let's move on to part C, where we're going to find X when Y is equal to 12. So we've got Y equals K on X, which means Y equals 60 on X. So therefore we've got 12 equals 60 on X when we sub in 12 for Y. So if I multiply both sides by X, we've got 12X equals 60, and then divide both sides by 12, we've got X equals 60 on 12, which is just 5. So therefore our value of X is 5 when Y is 12. So just like I did with the direct proportionals, I think we should make a note here. And that is, if Y is inversely proportional to X, then Y is equal to K on X. And we could also express that as X times Y equals K, right? But if I was to divide both sides by Y, we end up with X equals K on Y. And X is inversely proportional to Y as well. So just like directly proportional, inversely proportional is a two-way street. Alright, so once again it's your turn. So pause that video and do questions 1B and 3 if you have the new book, or question 4 if you have the old book. And when you finish that, we'll get on to the next section. In this section, we're going to be describing a journey by distance from home and comparing that to the time taken. So what happens to our position as time increases? So the first thing we're going to focus on is the distance from home. So if we're traveling away from home, the distance will increase as time increases. So in other words, the graph will have this general appearance, and as time increases to the right, the distance is increasing by going up. And when we're traveling towards home, our distance is decreasing while time is increasing. So we'd have the general graph where, like this, which sees time increasing to the right and distance decreasing. And a third possibility would be not moving at all, and we'd have a fixed distance in time. And that would have a graph like this, where as time increases to the right, distance stays the same. Then the second thing we're going to look at is the gradient of the graph, which tells us how much our position is changing. So for a straight line graph like this, we have a constant gradient, because it's always going to be the same amount of change for 1 unit of time. And then we might have a curved graph that has these different gradients on it. And these gradients at these different points are represented by this straight line that would pass through that point, and really it would be the curve for an instant. And you could see in the straight line, if we did the same thing, we'd end up having the exact same gradient everywhere. So these curved lines introduce the idea of a varying gradient. And for that curve above, it starts off flat and slowly increases. And the last thing that we check is the speed. And if you look at these two graphs here, if they were both to have 1 unit of time, the graph on the left covers more distance than the graph on the right. So you can see that this one here definitely has more distance. And that means that the steeper the graph, the more change per unit of time. And this is the definition of a higher speed. And as you know from our work with linear graphs, the change in the y value compared to the change in the x value is the gradient. And if the gradient is varying, then the speed is varying. So that means a line like this represents a constant speed, whereas a curve like this, at this point here, looks like the line is moving in this direction. And you can see that that changes as I move. So if I was to draw those gradients off to the right here, that means that the speed is decreasing, which is the same as saying decelerating. And on the other hand, if the graph curved up in the opposite direction and were to draw some gradients that mimic the lines at these points, we would see that the gradient is changing like this as we move along. And clearly our speed is increasing, which we describe as accelerating. Alright, so let's have a go at example 27, where we're going to look for these properties in the following graphs that I've prepared a little bit earlier. Alright, so this one here for A shows that our distance is going up. So our journey shows that the distance is increasing from home. And because it's a straight line here, that means that every one step I would change the same amount. So we have a constant gradient. And the speed, well, it's not a very steep line, is it? So we're definitely traveling at a low speed there. And because it's constant, we say it's a low constant speed. All right, let's move on to the next one. So as the left is our time that's starting, we end up at a lower position at later time, i.e. less distance from home. So that means that as this journey goes on, we're decreasing our distance from home. And just like the previous one, it's a constant gradient. So it wouldn't matter which part of the journey we measured. If we measured the same amount of time, we'd have the same amount of change in our distance. Now it's a bit of a steep graph, so you'd have to say it's a high constant speed. Alright, let's move on to part C. So you can see that we start at home, but end up further away from home. So our distance is increasing from home. And we can see that this graph is curving. So if we were to draw a gradient here or here, we definitely have a variant gradient and it's increasing. Oh, I'm running out of space there. So if we have an increasing gradient, that means that we're accelerating. All right, let's go on to part D. So we can see here that our distance is increasing. At time 0, we start at home, and at the end of the journey, we're further away. But once again, we have another curve, and to draw some lines through it, we've obviously got a variant gradient that's decreasing. All right, I prepared for that so it'd fit in. And because we've got a decreasing gradient, that means that we're decelerating. Okay, there's 2 more to go. And with part E, we can see that we're decreasing our distance from home. And it's a curve, so we've got a varying gradient. And if you look at these lines, because they're getting flatter, that means that our gradient is decreasing. So therefore we're decelerating. So don't get confused between the decreasing or increasing from home. What matters regards decelerating or accelerating is, are they getting flatter or steeper? Okay, so finally let's move on to the last one. We're definitely decreasing our distance from home. And when I draw in the gradient at different points, you can see that the gradient is varying and increasing. So even though our total distance is decreasing, we're accelerating here. So I know in the past a number of students get mystified when they first see this, but you do spend a bit of time with it, they should come straightforward. I'd also like to make a note here, because I just want to know if you've noticed that I've made challenges where you find one intercept of graphs of circles, hyperbolas and parabolas. Because the slope of that single intercept line at that point is the gradient at that point. So perhaps you might want to go back and have a look at those again. Anyhow, it's time for you to pause that video now and do questions 4 if you have the new book, or questions 5 if you have the old book. And then when you come back, we can summarize this lesson. Like many topics in this unit, today's lesson is not about difficult arithmetic, it's all about grasping a concept. And I can't stress enough how important this is going to be for VCE and university. Alrighty, so from today's lesson, a successful student will understand the relationship between two variables that are directly proportional or inversely proportional. Understand that the shape of a graph shows how a variable and its rate of change varies. Be able to use rules involving direct and inverse proportion, and know how to model and interpret a situation using a distance time graph. Alright, well done everybody. Got to the end of another lesson. There's only one more to go in this unit, so keep up that hard work. We'll see you in class, whether that's another video or the classroom. Bye.